This talk is quite short, but we're just going to go over the new rigid body physics features in Notch and how to use them that was released in the last release. Is everyone like completely exhausted? Oh. Just me then. All right. PC is now on. Okay, we're going to go through so what you can do with rigid body physics, how you set it up, and so on. So this was released in 0.9.21, and there's some examples in the sample pack already that you can load up and try. So we tried to make something that was quite easy to set up. Has anyone tried this yet? We tried to make something that was quite easy to set up. Yeah, seemed good. Yeah. The idea is that any 3D object can be turned into a rigid body and therefore act under physics and like bounce around and stuff. And cloners can also be turned into systems of rigid bodies. So this all works with the rigid body root node, which is a new kind of node. And so example node graph is something like this. So you have a rigid body root node, and everything parented to it can be in the same physics system. So like all those objects and the clones and so on are all part of a rigid body system. The rigid body root node is the parent of the simulation. So you can have multiple root nodes, multiple separate simulations that don't interact. And the objects have to be parented directly or indirectly to that root node to work. And then there's a new kind of clone effector called rigid body effector, which turns clones into rigid bodies. And then you can add additional like static colliders, force effectors, and so on to make increasingly complicated physics effects. So you'll notice under the 3D object node and primitives and so on, there's a new set of properties called physics attributes. That PC's dead, isn't it? Yeah. It's not my PC, is it?
No.
Good. Good. Don't fry my PC. The new set of physics attributes where you use these to set up the rigid body. We're going to do a live demo a bit later when that works. But for now, we're going to just go through what the properties do and roughly how you set them up. So the first property to keep in mind, to look at is the dynamics mode. So rigid bodies can be dynamic, which means that basically physics is on, they just act under physics, they fall and bounce around. Or they can be kinematic, which means that if you animate them, they can push stuff around. Or they can be static, which means that they're static. And they also have a bounciness property and a friction property. So bounciness is when they hit something, how much they bounce off. And friction is when they're like in contact with something, how much they drag. So the spin property on a rigid body is, there's an X, Y, Z properties for spin. And this is kind of like the inertia tensor, but what it really means is like how much an object is likely to spin on a given axis. So if I've got, I don't have any objects that are suitable, but if you had like a box, oh, here we go, I have some Barocca, right? So this object, if you spin it like so, it's going to spin really easily on the y-axis. But it spins quite hard. It's quite hard to spin on the other axes. That means you'd likely adjust the spin properties to make it more likely to spin on the correct axes. So you can weight how much it moves to get it to behave nicely. So the most critical thing about rigid bodies is the shape of the body. And there's several different options to set up the rigid body shape. So you choose the rigid body shape. You can use primitives as like stand-ins. So you can use a cube or a sphere as the shape of the body. Or you can use the original mesh. So if you have a 3D object, you can use its mesh as a rigid body. Certain meshes work well for rigid bodies. A very small set of meshes work well for rigid bodies. So if your mesh is less than about 20 polygons, completely closed and convex, then you've got a reasonable chance of it working as a rigid body. If you have anything else, it's not going to work. So if you made a cube, then out of like 6 quads, not a tessellated cube, then it'll probably work, and everything else not so much. So instead, we have the ability to generate for you a mesh, a convex hull that will work well for you as a rigid body. So if you, and this is the default option for the for all the shapes. So you choose the convex hull option, and it takes your mesh and generates for you a shape that will work well for physics without you knowing or having to do anything. So I'm going to show you what a convex hull looks like. So here's a like the original mesh, and there's several options for the way to generate a convex hull for that mesh. So that's my original mesh, and those are the various generated convex hulls. You'll notice that they look nothing like the original mesh, but they work well, they're quick. But surprisingly, when you actually use these as in physics, they don't look too bad in simulation. And they're solid and reliable. This is really important, because if you use meshes that are not, if you use anything that's not a valid solid convex shape, then the simulation just explodes. It doesn't work at all. So you have to get the mesh shapes right. And this is not really unique to Notch. This is like every physics system in the entire world has this same issue. So it's good practice all round. Wow, we have a PC. Amazing. Thank you very much, Luke. So clones can also be turned into rigid bodies using the rigid body clone effector. There are some complexities with this, which I'll demo. But basically, once you add the rigid body effector to clones, it means they all just act, it takes over all their transforms. It takes them over completely. So you can't really do much with them anymore. But you can apply effectors after the rigid body, so you can have some, move them under physics and then move them afterwards with effectors on top. And if you do anything really strange, like trying to animate the number of clones, that'll probably blow up the simulation, so don't do that. And if you start out with all your bodies intersecting each other, that will probably blow up the simulation, so don't do that. There are other kind of colliders available as well. So generally, in physics, primitives and convex shapes make good colliders. And procedurals make surprisingly good colliders as well. So if you want to do something complicated as a collider, it's often good to turn it into a procedural and then use that as a collider. The single worst thing for colliders is like just trying to use a mesh, because we end up having to treat every polygon of the mesh as like a really thin collision surface, which means that stuff can fall through them really easily. So avoid this. Do anything else except this. We also, in 922, we've added, because one of the first things that everyone tried to do was plug in a Kinect and then push stuff around, and it was really difficult. So we added a special kind of collider for Kinect cameras, basically, for generating colliders from a depth image. So now I want to show a live demo of how to set up a really simple physics scene. Do you mind switching? I have already, genius. Right, so this is Notch. I'm going to add a rigid body. So there's a rigid body root node, and I'm going to add a 3D object, which has a shape. Put it up into space. And put the grid on. So if I play this, obviously nothing happens. So a box in space. And if I want to make that box now behave under physics, let's change it to dynamic. And it will fall down. And the important thing to note is if you want to reset the simulation, you rewind to start. So hit home and rewind. So let's add more shapes. Let's add two shapes. So I've copied and pasted. And let's do the normal so you can see what's going on. Okay, so now if I drop these two, you can see that they do kind of what you'd hope, right? And we can obviously build this up. So let's add some more. So it's pretty easy to set up a simple collision system. And I doubt there's any 3D objects on this machine, but you can do exactly the same thing with 3D objects. So let's try adding a cloner into this mix. So just going to do a simple cloner and do another cube. So I've got my, I'm going to do a grid of clones. Less on the Y, move it up. So I've got my grid of clones. Let's bring them a bit higher. So if I want clones to act under physics, I just add a rigid body effector. And parent that to the physics root as well. So now if I drop all these down together, you can see that everything they all kind of act under physics. If we move those around. So the easiest way to edit stuff when it's under physics is to, so I made an obvious mistake, by the way. I screwed up my own simulation because I started up with two objects intersecting each other. And you can see how that does weird things. So I'll take my own advice and start them not colliding with each other. And there's some properties in the physics root node to do with so I've got a default floor, which I could turn off, and then they all just fall forever. And there's various properties to control the speed and update rate of the simulation, which we'll come on to in a minute. So I've got here, I'm using a box shape. If I wanted to use like a torus shape, then it's generated for me a convex hull from that object. And I think if I view, and if I show rigid bodies, you can just about see it shows the rough shapes that it's generated for the things. You might ask why all these properties are grayed out. It's because when you're under, so this node actually will work like this. If I hide all of this. So you can do, if you want a really simple rigid body setup for clones, you don't need a rigid body root. You can just use the effector on its own. But if you attach it to the rigid body root, then it can act as part of a bigger simulation. I feel like I'm getting myself in a bad place. So so if I apply additional effectors to this, if I apply an effector underneath the rigid body, you can see I can post-transform the bodies. So that rotation that I've applied to those bodies is after physics is applied. Therefore, it doesn't affect the physics at all. It's purely cosmetic. If you apply it above, then it does something different. Yeah, it's actually nulled out. So it makes more sense to have it below. So I want to go through some of the reasons why physics simulations screw up and what you can do to try and improve the quality of them. So firstly, physics in real life is continuous. I mean, I guess to a quantum level, it's basically continuous. Like you can't put your hand through your table no matter how fast you move your hand, unless you are a wizard or something like that. But in real-time physics, it's stepped. Like you're moving something, and we only evaluate physics every frame, so your object is in a new position each frame. So it's possible for my hand to be above the table in one frame and below the table in the next frame and miss the table entirely. Which would obviously be bad news because it means that stuff would fall through each other all the time. So if you have bodies that are really thin and moving really fast, they can just miss each other. So you need to take steps to make this not a problem. So in the rigid body root node, can we switch back to, sorry, I'm going to be doing this a bit. In the rigid body root node, there's a bunch of properties for the update rate of the simulation. So if I set this really low, then you get a different result to if you set it really high. You do get a different result, I promise. So physics runs at a different frame rate to rendering. It runs normally at a much higher frame rate. So typical physics system is going to run at about 400 to 1,000 frames per second, whereas a render is probably 30 to 60 frames a second. So that means you get a lot more physics steps than you do rendering steps, which means that stuff's less likely to go through objects as it goes. But the more steps you have, the longer it takes to run. So you have to kind of balance the how accurate it is by how fast it is. The more steps you have, the more accurate it's going to be. There's a couple of controls here. So you've got the frame rate of physics, which I've set to 900. And you've got the min and max steps per frame. So this means that like every render frame, the limit of physics frames I can apply. So this is there so that if your render frame suddenly tanks to if you suddenly drop to 5 FPS for rendering, it won't suddenly do thousands of physics frames and make your render FPS even worse, and then get trapped in this cyclic descent of physics taking longer, making your render taking longer, making your physics taking longer, until everything grinds to a halt and your server crashes. So this is there to limit that. Can we switch back again? Sorry. So that's one way to solve this. You just fix the update rate so you can reduce the likelihood that's happening. And the other way is you just make stuff move slower, or you have thicker bodies and so on. The next issue is this. The cube is supposed to be sitting on the floor, but it's jittering, right? This is a general problem with most physics systems in the world. They're all prone to jitter. And there's a few reasons why physics jitters. One thing is your frame rate can be unstable. If your frame rate's varying quite a bit, then it will almost certainly make your simulation jitter. So it makes sense to lock your frame rate down hard. And bad collision shapes can really make a mess of things. If you have a physics shape that's not closed or anything like that, then all kinds of odd things are going to happen. And if bodies start off intersecting, then again, simulation will have problems. But then once you've eliminated all those issues and you have a good physics system, you can still be prone to the resting jitter issue. So the resting jitter issue is bodies that a cube sitting on the floor, you think it's idle, it's not doing anything, but it isn't. It's moving all the time. So in a physics system, a box sitting on a floor, what's happening to it is every step, gravity is pushing it down. So it's an acceleration is being applied to that box. It's moving downwards. And at the same time, it's hitting the floor, and there's a collision response pushing it back up. And in the real world, these things perfectly cancel out to a microscopic level, so you see something that appears not to be moving. And in a physics system, in a graphics simulation, they don't completely perfectly balance each other out. So your cube sitting on your floor just wobbles a little bit. It sits there slowly wobbling because the two terms don't perfectly balance out, no matter how hard we try to make them balance out. So there's a couple of solutions for this. If you switch back again, sorry. So there's several parameters on the physics solver itself, on the physics root itself, that can help this issue. This is actually pretty stable, but we've got dampening and smoothing. So what smoothing does, so I've just smoothed the simulation, and now you can see it smooths the movement of the bodies. So the bodies are still moving, but the visual thing you see has been smoothed. So the bodies are no longer rendered in the place they actually are. They're rendered in like a smooth version of that. And then there's dampening. And what dampening does is every frame, it reduces the force on the bodies. So it makes them, so instead of falling under gravity, you can see their velocity's been damped constantly to make them slow down. So that is, those are one of the ways that you can reduce the jitter. But the most important way, actually, is this time till idle parameter here. So what this means is when these cubes hit the floor, like they just have, they don't move very much. They move a little bit, but not very much. And what we do is we track the movement of each body. And if it stops moving very much below the distance of this parameter called idle movement threshold, if they haven't moved any more than that distance for a certain period of time, we just say, stop updating that one now and leave it where it was. So it goes idle. And the good thing about it going idle is, firstly, it doesn't move anymore, so it doesn't jitter. And secondly, we don't have to update it anymore, so it becomes faster we don't have to deal with that body anymore. And if another body comes along and hits it, it'll automatically go not idle. It'll automatically start updating. So if you manipulate these parameters to roughly fit the scale of your simulation, then all will be good. But if you get this wrong, so I've just set my idle thresholds wrong, the bodies are no longer moving at all, which is obviously not what you want. So you need to adjust the parameters to make them only be pushed to idle when they really look like they're not moving. I can switch back again, cheers. So there's loads of examples in the 9.2.1 release package already. Things like using multiple bodies to interact with each other. Some quite interesting various setups here that you can go through. So all those samples are in the package already. So I'm going to finish with a couple of frequently asked questions about our physics system. First question is, why didn't you just integrate Bullet or Flex or any of the off-the-shelf systems that you already have? And the reason is, like, obviously, not coding stuff would have been great if we had that option. It would have been preferred to just pick a system off the shelf. But all of those systems we couldn't make them interoperate with the rest of Notch. So things like cloners in Notch only exist on the GPU. And all of these physics systems need interaction with the CPU. So we just couldn't make it work, so we had to write our own. What kind of performance you can expect? Our physics system is not targeted at like Minecraft style blowing up an entire world. It's targeted at the kind of interactive use that you frequently see in like motion design interactive installation projects, which is a sort of excuse way of saying it's not completely terrible, but it is improving in performance over time, i.e. it could be better, but it's still decent. And finally, can you bake physics? So in 9.2.2, you can bake clones in general. So if you switch me back again, sorry. On the cloner options, there's an option to bake clones to an animation. So for clones, at least, actually under physics, you can just you can bake that out as an animation and just play it back. So you don't have to simulate it real time. If you want perfectly replicatable, consistent results, you just bake it out and run it back. We're really behind time, so I'm gonna. Sorry, that was super quick, but thank you. Any questions? Yeah.
Do you have any best practices for position hierarchy of rigid body, I had a couple of issues. I had moved the placement of the Shape 3D versus the cloner position, and then ran the simulation.
So they're roughly evaluated in, it shouldn't really matter, actually, but they're roughly evaluated in order.
Is there a best practice then?
No, the order shouldn't really matter at all.
The format of the bake sequence?
It's our own format. If you wanted to bake, like you could bake clones to Alembic though. You just do them as geometry. You can bake them out to Alembic now in the next release as well.
Bake simulation with bake stuff system. How is that stored on the server?
Bake simulation. It's just we just have our own format, like our own stream format. So you can, it's like quite lightweight.
Is that stored as data or is it rendered on GPU?
It's all it's simulated to, because all the physics runs on the GPU normally, but when it's baked, it'll just be streamed in and run on CPU. So it's very lightweight.
Is there a way to set an initial state so where you have your intersecting mesh with a floater, like towards the explosion? Is there a way to that first frame where it's processing with that part, set that state to be all the layout for the explosion?
You kind of have to just lay them out so they're not intersecting in the first place. They will pop out they will de-intersect immediately, but probably not in a way that you might want them to.
You also mentioned that procedurals work really well with it. What's better, a particle driving a procedural, or does it work well with particles as well? Does rigid body work well with particles? Or do you have to drive that into a procedural?
You could. We don't have particles affecting rigid bodies yet, but you could turn them into a procedural. Yeah. Yeah.
Cool. We're going to need to wrap there.
Oh yeah, I'm getting booted.
Yeah. So, firstly, a round of applause for Matt.